Fine. Yeah.
Great.
Please do continue.
Okay. So great. Okay. Yeah. Thanks for having me again. So this is part 2 of this 2-part lecture series for today. Causality for Machine Learning 2. Again, for everyone who's maybe joining now, my name is Matej Zejcic, and yeah, happy to be here at the SSDS 2022. So, what did we do so far? Well, we had earlier Causality for Machine Learning 1, and we explored some of the, these basic concepts. But now we are going to explore some cutting edge and ongoing research, some selected publications and ongoing work, which is really at the interface of causality and ML, or AI in general, right? Yeah, today's session will be the same length as before, including Q&A till approximately 12:15. We might be around 12 plus minus, and then see how many questions there are. Again, please interrupt me at any time. This session is going to be quite different from the previous one in the sense that this is not going to be about some stuff which you'll find in lecture books, but rather in papers. And some of these things are still ongoing work in progress, so please also take them with a grain of salt. Yeah, other than that, in the afternoon, again, just to highlight, from 1:30 to 3, we'll have a hands-on session with actual code. And all of this will be available, right? Like there's a GitHub repository, I believe it will be public, and probably the links will be sent on Teams here. Cool. Then let's get right into it. So I told you earlier about this causality discussion group that we are having weekly, and actually many works, on this interface of causality AI/ML have been, discussed in this causality discussion group, CDG for short. And just to highlight some of them, right? Like we had even, Bernard Chukov's paper being discussed by, in this case, Anirudh Goyal. We had talk about self-supervised learning by Julius Kürgelgen. But also just yesterday, actually, we had this session with Johan Bremer. And I mean, some of you might know Taco Cohen from all the geometric deep learning. And so, yeah, quite the prominent folk and also people, who have been dwelling in other areas who are now pushing more and more into the causal direction. That's another Turing awardee, Yoshua Bengio, right, who's famous for all his work on representation learning, on general deep learning, right? So yeah, many works are there, and the recordings are freely available, right? So this is why in this session we'll be focusing on work from our lab, right? So again, CDG, the links will be there. You can find the recordings, and they're free, and of course the papers naturally discuss their papers best. And therefore, in this session, we will talk about some of the works I've been involved in our lab. Yeah, so let's get right into it. So, as the title of this school, right, it's data science, causal data science, but in general, that's really data science, right? And a big part is that explainable component, right? And earlier in this week, we had presenters who were talking about attribution methods and these kind of things, right? So everything which falls into XAI essentially, and now we are asking ourselves, well, what happens if we somehow want to do this causally, right? And yeah, this is the first part. So here we're going to explore this work. It is currently under review at ICLE, and really it is about this common ground between machine learning and causality, which we actually get naturally out of XAI. Remember, XAI just stands for explainable, right? Like explainable AI. And yeah, I'll always be referencing, the people who have worked here in this concrete case. Here it's Devendra, Konstantin, and Christian, my advisor. Yes. So all of it starts with the following kind of thought process or hypothesis, right? So what we call it here the HMM, not to be confused with the hidden Markov model. It's the human mental model, right? So do I have it written out here somewhere? No. So I'll just write out human mental model. Oh, no, the overlay of the screen is affecting me. I'll just write it down here. And what we mean by this human mental model is simply, your thought process, right? Like all of us have some kind of thought process, you know, when thinking about any kind of problem of interest or scenario of interest. And really what we're saying is, okay, whatever this human mental model is, right? We can actually convert it, or we can actually represent it by an SCM, by a structural causal model. Remember in today's earlier lecture in Causality for Machine Learning 1, we discussed what the SCM is, right? And that it's really at the heart of the Pearlian notion of causality. And now what we are trying to do here is establish this cognitive science view, right? Because at the end of the day, you know, explanations, they are linked to humans, right? I mean, we still don't even know what really good explanations is. I mean, that's been a problem for philosophers and cognitive science for a long time. And some of the answers you find in XAI, what we have seen earlier in this week, right? With, you know, I don't know, there's say a dog here, right? And now you want to classify this as a dog actually, and then it should mark and highlight this area in the image with the attribution, right? And that's an explanation, but is that really an explanation? I mean, you could say it's like a child, you know, pointing a finger onto something, right? And not even being able to say anything, right? But I mean, for the sake of what XAI has been doing so far, or at least these attribution methods, it has become widely successful, right? And I mean, that gives it merit. It's just one specific instance of, you know, what these explanations can be, right? And so that's kind of the setup, right? So you see that here's this person Hans, right? And Hans is having this, you know, thought bubble. And what is it? Well, it's an SCM, right? It's an SCM where you see there's property like the age of a person, the food habits of a person, the overall state of health and mobility. Yeah? And for example, you know, Hans might have this kind of imagination, or rather, let's put it like that, right? Hans will very likely not think in terms of equations, right? Hans might very well just think in terms of, you know, a structural, right? And the S again, and the SCM, the graphical, the causal graph part, right? And might imagine something like, okay, you know, age is going to affect the food habits and obviously the health, because the older I get, the somehow it will affect my health, right? And usually in a negative sense, right? Because, you know, getting older usually means deteriorating functions of health, right? And then you might say something like this, that health also has an immediate effect on mobility, right? And that's just, you know, Hans's reality, right? Like, that's the thing. Like, what really is nature and reality is a different thing than what Hans is imagining. But what we all we are saying here is that really this thought process that Hans is having can be represented by an SCM, right? And ultimately, even Hans's intuition like this could have some structural form, right? Which is what makes the SCM at the end. It's not just the graph, it's the structural equations. They imply the graph, right? So now we look here and we find, for example, this data point, and this is, you know, the mental model of Hans, right? And you see this Mafrak is this whole space, right? It's this whole space of all possible SCMs, right? And Hans's one is just located here. But now we say we have also different people. We have someone like Kurt and Jonas, right? It's a bit biased towards German names, I must admit. and yeah, they're also placed here, right? So we have, for example, Jonas and Kurt. And they are related somehow in that space, right? That's always saying. For example, if you imagine that you have a linear SCM, right? So again, you know, as we had earlier, for example, for VI, and then the parents of VI and some noise term UI, then what that means is just that, you know, F is somehow decomposable as some kind of sum over the parents, right? That's all what it's saying. And if we imagine that, right, I mean, it's just an assumption we make for actually proving our proposition. But in general, we just want to get this argument straight, right? And what this then allows you is to measure distances, right? You have a metric space, right? Like you have the space, you have this M, and you have a distance measure, this D function here, right? And in this case, what it'll tell you is that Hans and Kurt lay further apart than Jonas and Hans, right? And And you can see now here, for example, for yourself, I mean, Kurt is someone who's maybe abusing drugs, smoking a lot, whatever. Jonas seems like a fit guy, whatever. And certainly Jonas and Hans, the elderly Hans, who's more experienced, they kind of agree a lot on parts, while the Kurt is the rebel guy, right? And this naturally gives you this relation of where these points are located on in the space. Yeah. So, and naturally, one thing also to note, it's not shown here, right? But there's some kind of M star, you might say, right? And M star really is a nature, right? So it's really what is true, right? Like it's the true causal mechanism of how, health is being, dictated by, say, age and food habits, right? Like it's really what caused the biological processes in this case. Yeah? And of course, we can then again also measure distance to that one if we had it, right? But usually we don't have that, right? And so we cannot measure this directly, but we try to optimize it still, right? Because we're actually trying to get there. So this is the setup for what we call, this human model hypothesis, the HMM hypothesis, or just HM maybe for short, to not confuse with the Markov model. Okay, so what do we do next? So again, these SCMs, they are usually unobserved, right? So that's why this is the gray box here. But this is, what we just call the M star, right? And now, when you simulate this M, right, or nature does it for you, then you observe some data, right? And in this case, say we observe again Hans, yeah, or we actually look at Hans, right? Hans is in our data pool, and we look at him. And then we observe values for him, right? Like these are now numerical descriptions, again, age, food habits, health, mobility. And what this shows you now is, for example, Hans is of age 62. That's a very natural, kind of encoding of age. But now food habits, of course, food habits is 75, right? But that's just some representation, right? It's telling you just that, if it's on a scale from 0 to 100, as in this case, for instance, it's telling you like, okay, it's good food habits, right? That's what it means, right? And then the same goes for, health and mobility, which is seen to be lower than for example, the values for food habits. And so now if you look at the whole population, right, and measure the mean, right, so just the empirical mean, for instance, of mobility, then what you'll observe is the following, that the mobility of Hans, right, that it's smaller than the average, right? We're not showing the average here now, but just imagine, right, it's definitely, greater than 39, right? So and what this ultimately concludes is that this is actually, this assertion is kind of a question you're asking, right? Because you look at Hans' mobility and you see it's kind of below the average, right? Like you look at population and you look at patients and they all have some kind of features, and now suddenly you see someone who's falling out of this, right? Like who's below average, maybe even, significantly on some kind of measure, yeah? And ultimately you come up with this question. You ask, well, why is Hans' mobility bad, right? Like, why is it below average? And so we propose the following. Say you observe, well, not the SCM, but as we have seen in Causality for Machine Learning 1, you might observe the graph. And say, just for the sake, you actually observe some coefficients. Say it was a linear SCM, right? We don't have to necessarily make this assumption, but if it was a linear SCM, then say you observe simply like, for all of your variables, some coefficients, alpha, beta, gamma, and so on, right? And then visually you can just depict it like this, right? Like you have these G's for each of these pairs, right? And you know the structure. So what can we do with this? So we have this green box, and we have the data, and we simply ask a question, right? Like this question, we derived from the data. What can we do with this? Turns out for XAI we can do quite a lot. So this here now is what we call the structure causal explanation or interpretation, which takes as input the query, our knowledge and the data. And it can now give you onto the question, why is Hans' mobility bad? This answer automatically. This was essentially our contribution here, which is, well, Hans' mobility is bad because of his bad health, which is mostly due to his high age, although his food habits are actually good. And to decompose this now, you can actually look at it very nicely in the graph. It means you see this red connection here. When the health is usually higher, then mobility is also higher. And so if you observe mobility a bit low, that means it could have only been because health was already low to begin with, right? And so that's where you start, right? And it's also the chain that you're going, right? Like you have these different trajectories you go through, right? For example, you see the edge between A and F is not really important in this case for explaining M. And then what you also see is that there's the difference between the red and the green. For example, food habits. If you have good food habits, it'll have a beneficial effect on health. But health was also bad, as we observed for Hans, right? And so we can say, well, it's not due to the food habits, right? Because if you have good food habits, well, it should affect your health positively. So in this case, this is a green note here, decoded. And then finally, what we can also differentiate is here, the arrow sizes, right? So we had this little bit here called mostly, right? So it's suggesting that, well, although, age and food habits are both kind of things which directly influence the health and through that transitively the mobility, it is age which is having the bigger effect, right? So what you can imagine is something like, say you go to the gym, right, and you work out, and then you hurt yourself, right? Well, if you had a car accident, then on average you will be more hurt, right? And so naturally both would be causes, just like here age and food habit, for your hurt, but obviously the car incident would have a lot more impact, and so it would be certainly stronger as the cause. It's well also noting here that in general, right, like transitivity and causality is not really given, like in the most general cases. And also what we don't talk about here is maybe what you'll see also in cognitive science regarding, counterfactuals as we've seen in L3, right? But what this is doing is it's really just using the F from the structural equations, right? The set of all these, Fi, and using those and how they relate for each of the pairs to conclude this answer, right? So just to give the full overview view again, right? So SCM is not observed, but you have some data. You look at the data, you ask a question, you have some kind of assumptions about the graph, some expert knowledge or whatever, right? I mean, it could just be, this could be a doctor, right? Like it could be a medical doctor actually, who has patient records, right? And then sees Hans is bad and has some kind of, imagination, right? Some kind of mental model, which again, through this HM SCM hypothesis can simply be represented as that, right? And now you use all these three things and you come up with this answer, right? So again, why is Hans' mobility bad? Well, because of his bad health, mostly due to high age, although food habits are good, right? And now if you kind of start comparing this to say what we saw earlier with the attribution methods, right? I mean, you be the judge, right? Like it's not, I mean, it's certainly for a different kind of thing, right? But I'd argue that people would prefer this as an explanation. It's both a natural language and it's actually using these causal relations, making it automatically causal. Because one big fallacy of these attribution methods, for instance, is that say there's a watermark here in the corner, right? Then the attribution might only look at that, and that's actually wrong, right? That will be right. So these kind of things you automatically can kind of save upon here, right? But then again, as we'll see later, great thing about these kinds of things is of course the learning aspect, right? It's like super efficient, right? So or as always, trade-offs, right? But this is kind of this initial work we're pushing here. So now a little bit of maths, right? So I'll just guide us through a little bit. So it looks intimidating, but it's really, really simple in this case. So we have simply these different rules. So we define, first order logic rules, yeah, R1 to R3. And don't confuse them, right? So we actually adapted the notation here, but this is an old slide, unfortunately. But these ones, these R1, they are element of something like an ordering relation, like smaller or greater, while this R1 calligraphically written is really just a rule which makes use of these things. And what it's really just saying is that you look at a certain pair y and x, right? You look at the coefficient, you look at the sign, whether it's, positive or negative, right? And then just use your smaller, greater, whatever, to check whether it's, above zero or below zero, right? That's really what you're doing. And then you are having here this logical AND with this disjunction clause, with this OR clause. And what this really tells you then is, if we show it for an example, we'll just do it in a minute, but it's really just the generalization of what we discussed, right? Like if something has a positive effect and now you observe it though to be in a low state, then that means that the other thing must have been also in a low state, right? Like you see this counterfactual, at least, in terms of speaking, we have that, right? Like it's naturally causal. And these two rules are really just mutually exclusive. So, either one of them fires, right? And this will then dictate, a unique code, which actually gives you this explanation we just saw earlier in natural language, right? This is just the nitty-gritty technical details in a sense, right? And R3 is this preference thing, right? Like if there's more arguments, then just take the biggest effect one, right? That's really what it's showing here. And then the algorithm, right? So this is for computing these interpretations or explanations, right? It's just recursive. So you see, you just check at the first node for all the parents, and then you go recursively into the same function again, but now starting from the parent, right? And eventually, of course, you can prove that this, always terminates. Eventually, you come to the base case because, if we imagine here, so we start with MH, right? Now we look at age and it's the health and the age and the food habits. And now we go recursively, and now here, well, there is nothing here anymore, right? Okay, here actually there is, right? But then you come here and again you're at zero, right? At the empty set. So that's really how this algorithm is essentially working. And just to give an example here, so we start with the query at M, right? So we go here, and now we look, right? And we see that rule 1 evaluates to -1. And what does that mean? Well, if we just go back, then you can actually check for some choice of smaller and greater. If they're different, this condition will hold, right? And it evaluates to -1. And the -1 and 1, it comes from whether it's this case or that case actually. And here what we can see is health has a positive effect on mobility. The better the health, the more the mobility. But since this was low, this must have been low as well, right? And that's really what's coming out here. And then you see here's the recursive reminder for age. You're checking age, and then you go for A and F, and then the same game, right? Same game until you reach the base case. And then this thing here, right, is really just a code, which is telling you in this case, 1 here, alongside these, causal pairs, right? So this was MH, and then this was HF, and then this was HA, and so on and so forth. And then through that, you can actually decode this naturally, right? So of course, these words, these structures, right? These word segments need to be given, right? But like that's trivial. Yeah. And so, one thing we of course show is that, any, graph induction model, or what we called in the first lecture, the causal structure learning, that really any of them is interpretable or explainable in this sense, right? And that's just a natural consequence of the fact that most of these methods just, model some kind of adjacency matrix, right? Which then, translates to some kind of graph, right? So that's the setup. So now we looked at different, empirical stuff, right? And here what we see is now we check the quality of these learned interpretations or explanations, right? However you want to call them, even this phrase, right? I mean, it feels more like a stylistic choice at this point, because even there's, it's cyclic definitions usually. Any case, so what we see here is different graphs, different ground truth graphs. So here is, a data set with altitude and temperature being measured. This is the data set we just saw, right, with the age, nutrition, health, and mobility. Here's the one with cars, the tank size, fuel saving, driving style. And here's the classical one we've seen in CML1 with, treatment, recovery, and so on and so forth. Okay, on the left, you always see the ground truth. So you know that's always the true graph, right? And on the right, you now see what was learned, right? So everywhere where it's written identical, we perfectly learned the ground truth. Everywhere else, we see the differences. For example, in this one, we see there's an added edge here, and he kind of flipped the sign on this one. Yeah. Well, you would now think that now this is actually super cool, right? Like if you look now at the actual, you know, the eyes, right, which we just defined with our algorithm, then you can quickly see that something is wrong. But not just that, you can actually tell that it's quite drastic, right? Like for example, you would just, for example, this edge that it's flipped, right? You would not think that that's a bad thing. I mean, if you just see an adjacency matrix and it's not written one, but like minus one, I mean, you'd be like, okay, sure, whatever. What does that mean, right? But these explanations actually reveal this thing a lot, right? Or even like these added edges, like false positives, right? I mean, they're super strong. And so now if we compare here, the ground truth, again, remember, so his mobility was bad because of his bad health, mostly due to his high age, although his food habits are good. Now you look at the learned one, the blue one here, and you see he's saying something like Hans' mobility, in spite his high age, is bad mostly because of his bad health, which is bad mostly due to his good food habits. And you'll be like, wait a minute, this doesn't make any sense. Well, it doesn't make sense for you because your mental model, your causal model is closer to that one than it is to that one. But through this explanation scheme that we have, you actually reveal this like pretty quickly, and you can actually use it for debugging in a sense, right? This is one thing we imagined, this whole setup in like a causal explanatory interactive learning setup. Just to compare some of the others, so here it's very simple, you know, for example, you know, why is the temperature at the Matterhorn low? Well, it's low because of the high altitude. You go higher, there's physical mechanisms, and it gets colder. Yeah? Or why did Kurt not recover? Well, he did not recover because of his bad precondition, although he got treatment. And here's one example where the learned one, right, looks also quite different, but here it's, you know, we can also see it's showing here, right? Because it's thinking that the preconditions were actually affected by the treatment, which is, well, it's a precondition, it's not. So here what we have seen is just, you know, the quality of these learned explanations when using algorithms to get the causal structure, right? When you use causal structure learning. Now, in this other experiment, we did something interesting. We asked ourselves, well, what would happen if some of these explanations just lie around, right, as some kind of data, additional data set, right? Like your augmented data set, you know, your regular data set, plus these, you know, interpretations, right? Could that maybe improve learning, right? So what we did was just adding a naive kind of regularizer or additional loss term to the objective, which you know, computes and compares explanations to existing ones, right? Like it's as we had earlier with the semi-supervised learning, it's all the cases where you actually supervised, right? And so what you see now here is the ground truth graph. And again, remember, you can always, you know, depict this as a matrix, right? So you see here, this is from A to J, and again, A to J, and then there's, for example, this blue one, which might correspond then to this edge maybe, yeah. And this is the ground truth graph. And now we have two settings where we use ones with and without the explanations. So this is just the standard learning. And this is now when you say that the model must, you know, explain what it has learned with the framework we've provided, right? And our kind of hypothesis here was, well, if the explanations make any sense, then yeah, I mean, the model needs to be forced to be consistent, right? So, and that should get you closer to the true model because, well, the explanations contain knowledge about the true model, right? It's hidden in there. And it's something that a human might give you, right? Or any other algorithm for that matter. Yeah? And what we see here now is just that we actually observe in this simple setting with these random graphs, we see an improvement, right? Like as our intuition suggested. And what I really feel nice about this example here is, for example, you can see here that the incident nodes into the node H, right? I mean, there's really just one coming from F in the ground truth, but here H is connected to everything, right? And this gets so we lose that one actually, right? In this one, but all of these, there's a lot less false links, right? So and also, for example, here this edge, right? It's missing here, but here it gets recovered now, right? So certainly there seemed to be something happening here. Finally, for this one, what we did was we did a human user study, and that was actually pretty cool because, to go a little bit, with the AI machine learning community also towards cognitive science, which is ultimately also just the quest for intelligence. And what we did was, we provided these participants. We had 22 of them with common settings, common sense settings in a sense, right? So something like the altitude and what the temperature would be in, say, Celsius or whatever, and it would not be data, but it would just be the question of is the connection this way or is it that way, right? So just simple things. And what we show here now is the two ways of aggregating the human consensus in a sense, because what you'll get is for n times the graphs that you have been studying, say D, right? So you somehow need to merge them again into just n estimates, right? And what we did here was, one of them was simply looking at the frequency. For example, if there was overlap and this graph was predicted most of the time by people, right? So here you see the treatment and the recovery one. So people mostly said that treatment has a positive effect on recovery, and the preconditions have a bad effect, or like a prehistory. And here on the other side, we did a greedy approach where we looked at each of the edges, right? And always selected the one which is with the highest activation, right? Like which is preferred most. And with this, you get an estimate of what humans think, right? And now we did a comparison, right? Like we could just use our SCI SC algorithm, right? And compare now humans against machines, right? And well, what do we find? The humans just give what we had earlier as the ground truth answers, right? And the machines we saw earlier, well, they can do some nonsense, which again is also kind of like a indirect proof of, or evidence at least, for the fact that we do causal reasoning and these things still lack in that sense, right? At least in an awareness sense. So then we are going now to part two. So part two for this second lecture is gonna be some works on recent models, right? Foundation models, large language models, as they have been coined by the Stanford researchers, with all the impressive results. I mean, also the image-based ones, right? I mean, they're popping out every other week now, and how that relates to causality, right? Because there's a lot of ongoing debate of whether these, LLMs, whether they actually understand or whether it's just remembering facts or what it is, right? Like at the end of the day, these models are learning the statistical properties of the data, but they are trained on like really big data, right? Like that's the thing, right? Like so many parameters, so many data points. So this work was co-first authors with Moritz and Dave and Christian were also on it. So here we asked ourselves, well, can foundation models talk causality? There's also a follow-up work coming soon now on this one. This was still a workshop version where we dive a little bit deeper. But just to give you an intuition on this one. So we discovered in CML1, right? So there we talked a lot about these causal assumptions, right? And classically it's something like this, right? You have that there's maybe, as we saw with the Reichenbach common cause principle, that some confounder Z is affecting both X and Y, right? And in words, it would be something like Z is common cause of X and Y, but also the fact that there's no edge here, right? Like X and Y are causally unrelated. So that's a classical setting, right? And with a classical setting, you can imagine something like this, right? Say X is chocolate consumption in a country, Y is denoting the Nobel Prize winners per capita, and Z is the GDP. And what you can find actually is there is, if we have now X and Y plotted here, right? Again, chocolate consumption and Nobel winners, then the plot will look something like this. It will be super strongly correlated, right? Like it's a perfectly linear function, where you would have some countries like maybe China here and Switzerland there, right? And now you would imagine, just drawing the Switzerland here. So, and now you would imagine, well, does that mean now that, you know, X is causing Y, like eating more chocolate, and so should I just, you know, eat more chocolate, right, to get a Nobel Prize? I mean, sure, why not? Everyone would do that, right? But of course, I mean, we know that this is just a correlation, right? That's this famous example again. Spuriosity correlation does not imply causation, right? And there's a simple example because the structure is like this, yeah. There's a common cause, which in this case is the wealth of a country, right? You know, per capita, whatever GDP. And obviously Switzerland will be a lot stronger there with respect to this correlation, right? So it'll, you know, have both more chocolate factories and more Nobel Prize winners, right? And why? Well, chocolate factories because, well, it has the money to have these factories, but it also has the money to have the faculty, and they could get the, you know, statistically more chances. Now, what we thought in this work was, what if we actually have a, right? What if the models, the variables don't model actually natural concepts, but they actually model causal assumptions, right? So let's be concrete. So what does that mean? For example, X now is not modeling the chocolate consumption, but it's actually talking about the causal graph. It's saying something like, you know, C is a common cause of A and B, and A and B are unrelated, right? And then, you know, Y could be modeling a question, something like, does C cause A and B? You know, does altitude cause temperature? And then the confounder here would just be, you know, everything else in a sense, like description of reality. Like, I mean, we live in a reality where, you know, going up the altitude will you know, drop the degrees in Celsius. But it could be, I mean, we could imagine a different world where both of them go up, right? So it would be different mechanisms, but that's just, you know, what it could be. And so they could also be correlated now, right? They could be correlated. We could see that, you know, these assumptions and the corresponding questions could be correlated. But now this is a different type of correlation, it feels. It's like a correlation on top of, you know, causal facts and causal statements. That's why we say like correlation on top of causation here, right? So that's what we imagine, right? And that's very interesting because just stay here one a second. Essentially, if you have the this classical setting, right? Then of course the causal hierarchy theorem, which we have also seen in the first lecture today, which told you that, you know, you cannot go from L1 to L2 without assumptions. It would tell you, well, it's impossible, right? But now, what if our data, right? Like, what if the L1 actually is this? And now actually to be more precise, you know, we think it's L1, right? But it's actually L2, right? It's actually statements about causality. I mean, these things, this is a causal graph. This is L2 data, right? It's just coming in the disguise of L1 data because we just, you know, we scrape the internet and whatever, right? And so it turns out that the CHT, you know, I mean, it's perfectly valid, right? And so in this case, right, that would imply actually that these language models, right, if they have all this data and they observe these correlations, then they can do causality in a sense, right? They don't understand the causality, but to answer causal question then is not a question of whether you understand causality or not, but just a question of whether you not know the right answer, right? And so it's very reminiscent of, you know, old school computer science arguments like by Searle with the Chinese room argument, right? Going back to Turing and others. You know? So what do we look here at exactly? So you know, we had our foundation model, or in this case, just an LLM, right? This could be something like, you know, GPT-3 or from OpenAI, OPT, and so on. And now we just have the question. We have some variables X and Y, the descriptions, and we ask something like, does X cause Y? And the cool thing about LLMs is you can just directly query this, right? Or something like, is Y the effect of X? It kind of rephrases it, yeah. It doesn't imply it's the same, right? But you know, they are very similar. It might even be same. And then, you know, the foundation model will give you some kind of answer, which you can then process, right? Like here's a processing step, and then you might conclude this, right? So it's in a sense a naive way of doing causal structure learning, as we have seen earlier, with, you know, these language models. So, and what did we see? So this was an interesting observation. For example, we looked at, you know, these different data sets, and a lot of them you'll recognize from the previous discussion on XAI. And what we're asking here, for example, is, is there a causality between X and Y? Yeah. And then the model will answer with a bidirected error, essentially. It'll say yes, and then of course you draw it like that, right? In any direction. So it's suggesting there is a relation between altitude and temperature, but it's not decided which, right? But now, interestingly, when you ask, for example, does X cause Y, does altitude cause temperature, and vice versa, then it'll give you the answer only in one direction, not the other. So in the case of this, what we here now call asymmetric query, right? You actually get the model to decide, right? Like if you just ask it about, causality in a sense, it'll say, yeah, they're connected, but not specify how. But if you suddenly ask that, does this one cause the other one, right? Like just by doing this, you suddenly get an answer, right? Whether it's the right one is a different question, but you suddenly get a decision. So it's deciding between the asymmetry, right? And yeah, you can see a couple of also more like detailed observations we're having here. Yeah, and that's actually concluding that part. So that was a kind of brief interlude, with the language models, and essentially the conclusion was, well, they are not understanding. They have no explicit notion of the causal model, but they can still get the answers right, and it might be due to correlations. And again, we have some other work which is coming now. I don't have any slides on that yet, but if you're interested, please stay in touch or stay tuned, because there we are exploring how we might actually be able to measure these correlations. Now, another big topic we have been discussing a lot in our lab is connecting SCMs to other model families, right? Looking at their relations and what it could mean. And one of our works, which we published in NeurIPS last year, here with also Atresh and Shriram from UT Dallas, was on some product networks. So for maybe many of you, as I've experienced in the past, these models might not say anything, but I'll just give a brief tour on those. So that's an SPN here. And what you see is it's really just a DAG again, right? It's just a directed acyclic graph, as we saw in the previous lecture. And it has like these product nodes and sum nodes, right? And that's the name, right? Sum and product nodes. And what it really is a probabilistic circuit, right? So it's a circuit, right? It's a computational graph. And at the leaves, you have these distributions. And what it really does is give you something like P of X. And it gives you it properly, right? It's not just like a neural network function, which then has some kind of softmax or something, right? It's really an inherently probabilistic model. And the great benefit about these ones is they are actually tractable in inference, right? So asking a query something like, what's the probability of X being X, you can actually get this in linear time, right? In the size of the network. And that's a big advantage. Why have they not taken off yet? Well, it's kind of hard to scale them in terms of expressivity, right? So, when you look at, I don't know, images generated, from a neural network, they look very crisp, while for an SPN, it'll still be a little bit maybe, blurry, right? But otherwise, they have the advantages over neural nets in the sense that, they are super efficient and compact and actual probabilistic models. So, and what we did here essentially was we asked ourselves the question, just as we had now for the title of chapter 3, SCMs and other modeling families. Well, these are PCs, and what is the relation between PCs and SCMs, right? Probabilistic circuits and SCMs, or specifically SPN and SCMs. And here specifically, so this is a detail, so we'll go over this now. This is a special kind of SPN which actually also use a neural model. And in any case, you can also see this as a neural network, right? Yeah. So let's motivate again. So we'll see familiar faces, Hans, Jonas, Kurt, and this new guy. Some individuals, and again, we measure some kind of data. This is our typical feature matrix, and it could be anything, right? Here it's just patient records. And say now there's a vaccine coming out, right? And everyone is, being vaccinated, and it's affecting the health somehow, right? And say this is now a radical vaccine. It's not the great COVID vaccine. It's like something like here. It's affecting everyone randomly. It's resetting them, say, uniformly. Yeah, very brutal, but let's say. Then you see it's propagating its effect onto everything which follows in the causal chain, which is then also the mobility. Yeah, this is the setup. And so again, the hidden reality, the SCM is not given. Yeah, but it is there. It applies a graph and it applies our data. And now here the difference from top to bottom is just, changing the health to be uniformly distributed, in this case between 0 and 100. And as you see, as we have learned in the first lecture, it's really just replacing this. And what happens in the graph is the edges get cut, right? Like, because there's no dependence anymore. This is not a function of A and F anymore, right? Not, yeah. And it applies again data, right? And in this case, this interventional data. So that's the setup. And we have just seen these SPN. And the question was really, because SPN can do tractable inference, can we do tractable causal inference, right? And is there maybe a purely computational view on causality? Because if you think about it, right, like there's altitude and there's temperature, and this is your causal graph, right? Or your BN or FCM, call it however you want. That's semantic, right? Like that's just, altitude and temperature, and one affects the other, right? But now in an SPN, it's computational, right? Like it's something like, you have the sum and then the product node, and then here's the A and the T, and then the same on the other side, right? So from here, I cannot easily tell, or as nicely tell, this component here from the left side. And so this is really the challenge when exploring this topic here. And actually there was work previous to this, right? So Zhao et al. Discussed the relation between Bayesian networks and SPNs, right? And then, Papantunis and Bell, what they did was they used this method for their argument on causality, and they claimed SPNs cannot do causality. And while their argument is correct in what they show, it's kind of also a bit difficult, because what you get out is a degenerate BN. I mean, if I compile my SPN, right, to Bayesian network, say altitude temperature again, but there's no connection here, right? There's nothing there. I mean, of course, I cannot do causal inference, right? And that's what we kind of felt about this one. And so we said, okay, well, but still, it's going to be hard with SPNs. But what if we used conditional SPNs? And these conditional SPNs from the previous figure, they are really just SPNs which have a neural network which is controlling their parameters. Yeah. You don't have to understand all the details here now. It's really just about grasping the high level idea. And yeah, we looked at several of these experiments, and what we just can see here now, we have this different baseline. ISPN, I mean, you can observe there's some cases with high variance, but in general, any of the interventional distributions. Yeah. We also explored the causal stuff and just validated that it's working in a sense. In the interest of time, I'll just be skipping that one and going to another work, which was maybe our most famous work so far, in the sense that there was quite a buzz in the community, also on social media like Twitter. This was also with Petr Veličković from DeepMind, who is an expert on these models, on the GNN. Yeah, these are the models from geometric deep learning. And again, right, as the chapter suggested, what is the connection to SCM, right? Like that was really the motivation on this work here. And yeah, so there's a couple of concepts. I will not go into detail here now, just in the interest of time. But what I'll just say is, so we use variational. Variational inference is really just, you're usually concerned with these joint distribution, and then you want to learn this posterior. So Z is usually your latent variables, which you learn, right? X is usually the data, and now you want to learn from those to those. And one way of doing is via optimization, and this is then called, variational inference, where you select a family. For example, this here is a mixture of Gaussians. So you have something like, these kinds of distributions, yeah. And essentially, you just optimize the Kähler divergence between what you have chosen and the true posterior. And well, how do you do that? There's this famous evidence lower bound, or short elbow. Looks complicated, but it's really it's really not much. It's really just the main idea behind the variation autoencoder, right? If you've seen it before, right? An autoencoder is just something where you have your data, you have your latent code, usually a bottleneck, and then you reconstruct your data, right? And this is a neural network, and this is a neural network. That's all you need to know for this one. Also, I have just some references. I mean, you can always check out if you're interested, right? The slides will be shared. Then also just shortly, because that's important, of course, we are talking about the relations. So just like with the SPNs, we should just mention them a little bit. GNNs are really just neural networks, right? But which place, this inductive bias on a graph, right? So they structure their computation essentially following a graph structure. They respect the graph structure, and by that they use the information from the graph structure in the computation. And really, how it looks like is you have this permutation invariant function where the ordering is not important, right? So it's invariant to the ordering in permutation invariant, and permutation equivariant application, right? Like of these functions. So you have whatever this this ordering will be on the high level, it's just equivariantly commuting with it. And there's in general 3 different flavors of these GNNs. The most general is this message passing one, right? And it's also, if you have had probabilistic graphical models, you will recognize then this convolution because it's very close actually to the CNNs and attention, as you have seen in transformers and so on and so forth. And how does it look like? Well, in your graph, you have some variable I, yeah, and then it has some neighbors, and one of them might be J. And then really in the message passing, what you do is you compute this message in this psi ij, and then aggregate those. Aggregate those, have some kind of activation function, and you're done, right? Like you get your representation. So really, it's just, you can imagine like you have a graph, and then you start with your input x, and get out then your different kind of your latent representation respecting the graph structure. Again, also here's pointers. There's also really, I mean, Peter is really an amazing lecturer, so there's really cool stuff on there. So feel free to check that out. And yeah, now going back to causality. So how do we do it? There's this famous saying, right? So we have seen how important interventions are, and Peter Holland and Don Rubin went so far as to say something like, yeah, there's no causation without manipulation. It's not true, as we have seen. I mean, in CML1 we have learned about do calculus and how it is actually the savior in this case, but intervention are crucial, right? And we asked ourselves the simple question, well, what does it mean to intervene on a GNN? And then we were saying like, okay, let's look at where we can start, and we were like, the intuition is clear, right? There's a G in GNN, there's a graph, and the graph is implied by the STM, so it kind of makes sense to start looking there. And so we defined then an intervention in GNN, and really what we did was just according to what interventions look like in an STM, right? And modifying, in this case, assuming hard interventions, and getting the computation out. Again, you don't have to understand the details here. We can ask questions later as well, or I mean, interrupt me as always. But I think just getting the high-level glimpse here is already the best you can do for now. Yeah, and then I'll skip this one in the interest of time. But we were looking essentially at different model classes, model relations we could identify. And it was quite interesting because, for example, if you just look at the relation of SCM and GNN, well, it would be an expressive model, but it seems just infeasible to train, right? But then again, something which is easy to train is a model which is based on an autoencoder, but then you factuals, but that might be sufficient, right? So it's somehow this what we'll just show now, this GNNs with the interventions, they lie somehow in between say just a regular GNN and an SCM. That's really the takeaway here. And here just a comparison. So bottom here you have usually we don't note this, but with the M, right? So you have this structure causal model. It consists of all these structural equations, and then you get your causal effect. And what we do is we have this autoencoder structure here where these F and G are GNNs, and they are GNNs. and in this case, these IGNN, right, which allow for interventions. And you see, naturally, here we have only 2 models, while below we have 4. And I mean, actually, we have number of variable models, while here it'll always be 2, right? And so that's already a great advantage in terms of compression in a sense. And yeah, then you looked, we kind of validated. What you see here is this famous Asia Basin network, and we intervened, for instance, on this tuberculosis property, cutting the dependence on whether we know that the person is from Asia or not. By the way, this data set's anyhow very outdated, but I mean it's still, it's a great Bayesian network to look at. And that's what we see here, right? So we make it a coin flip. So you see here before, tuberculosis was pretty much certain, right, for these people, and then here it's a fair coin, and we see that our model adapts to that. But not just that, you also see that here it changes, here reducing, and also here, right? So it's really just capturing these effects, right? And that's what we showed here, that in principle these GNNs can do that, right? Okay, finally, then we have one more thing, which is another block, which is on linear programs and causal semantics. So linear programs come from mathematical optimization, and our intention was here, okay, well, they are super relevant, right? I mean, be it energy system modeling or anything really, they appear everywhere. Although they are so basic and we seem to understand them, it's kind of hard to explain them. And again, explanation in the sense of the cognitive science aspect that we saw in the first chapter. And still these constraints that you have them, and the meanings of the variables, and the fact that constraints can have meanings as well, kind of suggests that there's a connection to causality. And this we kind of explored here. This was joint work also with Florian, published at this ICLE workshop this year. And we really looked at how we can identify structure and causality in linear programs. So the high level idea here is the following. So you are giving a linear program, right? And a linear program is really just, you have this objective function of your data, you're trying to minimize that, and you have some constraints, ax smaller equal b, some linear equation system. And here in this case, x would just be, x1 and x2, and you see it's pizza and salad consumption. And now you see that you have also 2 constraints, C1 and C2, and they actually have natural meaning. This is what I just meant, right? Like this one means, calories, and this one means micronutrients. So essentially what just happened? Okay, so essentially what this tells you is that any point you'll find here will be essentially a diet which is satisfying these 2 constraints, and you could say it's healthy in this case, right? Like because it satisfies your micronutrients and calories. But it also depends, right? Because you want to optimize the cost, right? And for example, this diet will be maybe super expensive in this case, and so what you want to have is lie somewhere on these corner points of this polytope, right? And so yeah, what you then so that's what's given, that this LP, and again you see the gray box, so we'll assume for the moment it's hidden, right? But there exists some encoding phi which now generates what's on the right, and on the right is data. So imagine you had the data where there's a label phi, green denotes a healthy diet and red a non-healthy diet. Then you can say that, for example, this point here I've marked is a not healthy diet. You eat a lot of pizza and even a lot of salad, and that's just too much in general. And then say this, for example, is a healthy diet where you don't eat much pizza and a lot of salad. Yeah. And so you can imagine now you have this data set, and it's kind of giving you a little bit of a structure of the polytope, right? So you don't know about the LP, right? And you also don't know about this function, but you just observe this data. And now what can you do? And well, what we thought was, well, what happens if we just do, what we call causal structure learning, right? Or in general, just structure learning. Turns out you can get an answer like this. So you get a graph where you see there's no dependence between x1 and x2 as well, more or less expected. But there is directly onto whether the diet is healthy or not, right? So pizza and salad, dictates whether it's a healthy diet, and actually also because one of them is stronger than the other, pizza is actually worse for your appropriate diet, right? Which is, I guess, common intuition nowadays. And so this is really the general setup. And now we looked at different cases, right? So let's look at left first. So here you just have, your data and your label, and here we just validate it, right? We said like, okay, one encodes it's a feasible solution, so it lies inside the polytope, and 0 denotes it is outside. Now what you can see is that clearly there's a connection from all the x1 to y, right? And when we flip the encoding, then also here, as expected, the colors change, right? And we go from negative to positive. And so really what's happening here is we are using actually a method called no-tiers, NT for short. And what it does, it uses continuous characterization, like a cyclicity constraint. It's something like the trace of the matrix exponential Hadamard, to characterize that there's no cycles in a graph, right? That there's not such a thing. And then here we started looking at a more interesting case. So we said like, okay, what if we change the B, right? Like remember, there's this constraint A, X, and B, and what happens if you do that, right? So essentially, the B affects here this border, right? Like how far it goes inside, and you can clearly see that it affects the solution, right? Like it affects the Y, because if you shrink down the space, then obviously there will be more points which are outside than they are inside, right? And so this was also something which was expected. And I believe it's not at all, clear that, this should be happening if you do that. Here also an interesting one. So here we looked at a very general setting where the cost function, the constraints, and the solution, all of them, can be varied. And you see these patterns, right? Like you see these very interesting patterns. And what this really is just telling you is that, the structural learning algorithm is picking up on the rules of the linear program. And here's an interesting case where we looked at a special linear program. It's a shortest path problem, classical computer science. And what you can see here, for instance, is that something like x5 must be part of the shortest path, right? And this will be highlighted. You see that the highest activation we get here is actually from x5, which is the one which must be in there, right? So this was actually a pretty cool observation. Then we also had another work, and just briefly on that one, but again, linear programs, but now a third connection here. So it's the one with adversarial examples. So adversarial examples, just as a short reminder, again, if we have our dog, right? And then you say, well, this is a dog. And now I put some noise on it, right? So it just looks literally the same, right? Like well, I didn't draw it the same now, right? But it's just, it's pretty much the same. Just some pixel values are different. And suddenly it says something like plain, right? Like these were adversarial examples. And this is kind of shocking in a sense, because going to here, it's not just noise, right? It's not just noise. And yeah, so here really we show our example where you have a linear assignment, similar like a shortest path, right? It's in this case it's an assignment. You have people and their health records, and whether they should get a vaccination spot, right? So this was done during when the COVID pandemic was really on fire. And what you see, this matrix is really specifying a solution, right? Like which individuals should be prioritized. And the policy would be something like, okay, people who are in a risk group, right? They should be prioritized. Now, when you look at that, right? So you have this matching, and that's great. And now you look, for example, at a confounder, at something like wealth, like rich people, up here, poor people up here, down here, and then you see that there's a kind of more or less uniform distribution. Yeah. But now we inject some noise. and we get this W prime, this W hat, right? And you see, virtually, it's indistinguishable, at least to the human observer, right? But it leads to a completely different solution. And the solution will be similar in terms of cost, right? Like it'll be still, approximately that. But in terms of the confounder, right, which was wealth, you'll see now that there's this skew towards the wealthy, right? In the sense that, being wealthy allows you to let your connections play, whatever, and then, get a vaccination spot, right? All of them are still people who, require, that's the cost aspect thing, right? Like all of them are still people which require a prioritization, but it's just that they could skip this uniformity, right? And this is what we kind of show. We provided some, causal semantics on this, that this is a confounder, and when you have that, then you can actually do some noise on that and change linear programs, and that, this the code will be very different, right? Yeah, I guess this was a bit fast, but bear with me. This was just, again, highlighting some stuff. Finally, some just other directions, just really, that's really high level in this case, just to make you aware of some other stuff we have been looking at for AI and machine learning. One of them is what we call this loss, right? So really, I want to draw your attention to this and this, right? Here we see an example of these classical attribution methods for XAI, and now we can see that these objects of interest, they're marked better, right? Because they are the causal reason in our setting for what we are trying to observe, and the causal loss, similar to the semantic loss in neurosymbolic AI, is really trying to adapt the loss function in such a way that the learned neural network respects more these causal reasons. Yeah, that's really the high-level idea. Then another work here also by a recent master student, Salah. He looked at Bongard problems. So some of you might know them. They are, old school problems. There were originally 100 of these proposed by Russian scientist Mikhail Bongard. And what it's really about is you have these two sets of images, and there's one thing which is separating them, right? And you want to figure out what it is, right? So for example, in this case, it's actually not trivial. So you see there's a square shape. It's reminiscent very much of these typical intelligence tests and abstractions skills. And you see there's like a square and a circle, and now here it's a square and a triangle, and so on and so forth. And now you have to find out what is the separating factor here, right? And yeah, I'm not spoiling the solution on this one. Yeah, there's simpler ones, but there's even harder ones. And this is certainly one of the intermediate ones. It could just be something like, on the left you have all images in white, and on the other one on black, or in this case red, right? Yeah, and he was actually using the tools we have seen, and some other tools we unfortunately couldn't discuss in these two lectures, because there's just so much we could do. We could do a whole semester on this, but really just using causal assumptions on and a reinforcement learning setting to kind of help improving this thing. Another work related to this thing with these SPNs but also these just regular neural causal models, right? We looked at inference, and mainly what we concluded is that any kind of SCM, right, which will have some kind of parameters theta, will be intractable, and that's really a kind of sad conclusion. But what this really means is that like your PV and everything, it'll be even sharp P hard, right? Like we proved this as like complexity theory. And yeah, again, we come to the reminder of the announcement of opportunities following this school. Again, the discussion group, right? It's a weekly endeavor. You can find all the recordings in there, and I hope I could have sparked a little bit of interest in you. So please check it out. It's really open to everyone, right? Like even if you have not done anything here, and if you have done so, even better, right? Like, and yeah, and then also the workshop, right? There's this workshop on neurocausal and symbolic AI at NeurIPS this year. Unfortunately, you cannot submit your works anymore because right now we are in reviewing phase. but you can definitely just, join the virtual event. Right? And again, if you want to stay in touch, here's my Twitter handle. And I keep a blog with some interesting articles. So always feel invited to check them out. And that's a wrap. So that was Causal Machine Learning 1 and 2. And I'm happy to take questions. And in any case, see you also later to the final thing today, which is the hands-on coding session.
Thank you, Matej. I think don't see any questions. Strange. Okay.
Maybe everyone
probably,
understood perfectly. Yeah, that would be great.
This second part was really about new stuff, and you actually showed pretty much of them. But anyway, it's interesting because it shows that these neuro models and causal structures have a future. And in your opinion, which marriage will be most fruitful? Now you said you have shown SPNs, you have shown graph neural networks, which seem like structural causal models, but really, can you implement all the inferences that's let's say doable with I don't know, Bayesian networks or structural causal models into graph neural networks?
Yeah. That's a great question, actually. Actually, a question I was asking Bruno Gavranovic at his category theory for AI lecture. And he was just giving a general answer, which I find is correct in the sense that it's kind of up to preference on what you want to do research on, right? I cannot really judge like what will be successful. My take is the following. So you see these neurocausal models, you can compute with them, it's kind of intuitive, but training is really not the easiest. You need the data, and in general, the structural learning, I mean, because the DAX scales super exponentially, I mean, we have not seen much happening with more, right? Like we have seen some general structural learning with like 1,000 and so on variables, but then say some representation learning, it's not being done with like, it's only being done with like 10, 20 variables or so, right? So that's kind of problematic. And in general, right, if you think about it, like the Bayesian network stuff, right, like why did they develop the SPNs as a special class of circuits? Well, because the inference was a big problem. It's sharp P. It's not even NP hard. It's sharp P hard, right? Like you have to count all the possibilities. And so what that really tells you is that SPNs were need of the hour to have tractable inference, because it's one thing to have a nice looking model and a model which actually knows what it's talking about. But also, I mean, at the end of the day, you want to use your model, right? You want to ask your model a question. You want to know what is the probability of the weather and you today, right? And you don't want to wait like 2 days to get the answer, right? So that's why these circuits, these SPNs are super great, because they don't have an exponential blow up and are linear in the network size. So, and then since the network size will not blow up, it's super efficient, and they are actually also proper probabilistic models, right? Like they have the proper semantics and everything. It's just a question of scaling. And now the question is, I was asking myself, well, will it be that we scale them first? Which I believe, I think we'll scale them at some point. But then again, will we before that have neural networks which are more understandable or so, right? Like maybe from a category theory perspective where you can understand the simple building blocks, yeah? So I don't know what will happen. I think I think we should see it from a positive side. I think whatever you choose to study, it's worthwhile.
Yeah, that's true. Actually, is strange because it seems after so many years of machine learning and having theory, it seems that actually right now it's much more expanding than ever. So there are much more ways to research than we were aware, I don't know, 30 35 years ago.
I can, of course, not
so
speak
it's
about
like,
35
you
years
are
ago.
discovering
But
how much you do not know actually right now.
Yeah. No, I agree 100%. I mean, you know, at least the things I've heard about the past, I mean, it just makes sense as well, right? Because deep learning in 2012 with ImageNet and so on, there's, I mean, so much hype and also warranted one, right? And it's yeah, there's more access to through, you know, globalization and everything. A school like this, I think it's a great opportunity, and so yeah, the materials are out there. The success has been shown, so the industry has been interested in it. All the money is flowing in there, so kind of makes sense,
yes.
right? Yeah.
Yeah. Well, if there are no questions, I would call it the lunchtime, and we meet in 1.5 hours from now, I think, to show so that you can show us a bit of these tools that you use, tools that you have made, and what can be done. I forgot actually to ask you about, you mentioned probabilistic circuits.
Yes.
And actually, I would recommend also our students, there is a tutorial, I think, around on probabilistic circuits, because it shows you in a very elaborate manner how do you actually differ from neural networks. What can you actually obtain if you go this direction in terms of AI? In terms of queries, you can pose and get an answer which is much more than, is this a cat or a dog?
Exactly. So yeah. So what I'll also recommend there is, so just to write out the names. So for example, Antonio Vergari, he's currently at the University of Edinburgh, and also Guy van den Broek, he's at UCLA, where also Pearl, his university, and obviously Christian Kersting in our lab, and there's many more. There's Robert Perhatz and so on and so forth. I mean, just an incomplete list, but yeah, just a couple of names. There's nice tutorials, also very visual ones. So for anyone who wants to check them out.
Yeah, thank you, Mate. And then we see you again in 1:30.
Great. See you. Bye.